A very good afternoon to all. I'm Neenu. I'm a postdoctoral research associate with Tariq Ilahi in School of Informatics, University of Edinburgh. Today I'm presenting the paper Secure Key Transparency Protocols for Interoperable End-to-End Encrypted Message Systems. At first, I would like to highlight the Article 7 of Digital Marketing Act distributed by European Parliament, which is about an obligation for gatekeepers on interoperability of number-independent intercommunication services. This act requires that gatekeepers shall make communication services interoperable with other communication services. This act also requires gatekeepers to continue to provide end-to-end encryption to their own users as well as users of other platforms. End-to-end encryption relies on trustworthy storage, maintenance, and distribution of public keys of users. So it is very important for service providers to provide some key transparency solutions to their users because service providers may not try to cheat their own clients, but still they may be curious to listen users' conversations. Several key transparency protocols have been proposed in the literature, and various protocols have been adopted by service providers as well. Our work is based on, inspired from, I'll say, from Connix, which is where a service provider is maintaining a Merkle tree-based name-to-key directory. The service provider signed the root of the Merkle tree with the secret signing key and is keeping that at some public platform. This key is something which is dynamic in nature. It is updated whenever key changes happens due to new users join or maybe some existing users reinstalls the messaging apps. So if there exists a user, Alice, if she wants to talk to Bob, who is another registered user with the same platform, so she will ask for Bob's public key to the service provider. The service provider will reply back Alice with public key of Bob and some auxiliary information. This information helps Alice's device to regenerate that Merkle tree on her device, and then she can compare the root of the Merkle tree with the one that is available as the latest on the public platform. Only after successful verification, Alice's device can send an encrypted message to Bob's device. Now, this verification for public key of Alice can be done by Bob as well, and any other registered user of this service provider can do verification for their public keys on their own as well, for their own public keys. So if we see that trust issues become more complicated when we talk about communications and across interoperable cross platforms because Alice and Bob now belong to different platforms. So any of the service provider, whether it is senders or recipients, may try to equivocate the keys. Like in this case, Alice and Bob belong to different providers. So if Alice asks for public key of Bob, then there's a possibility that Bob's provider is trying to impersonate as Bob, and he's replying with any public key other than Bob's public key. There is also possibility that Alice's own provider is trying to manipulate the public key that he receives from Bob's provider. To the best of our knowledge, not much significant work has been done in providing key transparency solutions to users of interoperable cross platforms, and we provide secure key transparency protocols for interoperable end-to-end encrypted message systems. Using our protocols, users of different platforms which are interoperable can verify the consistency of public keys of other users, and they can do the end-to-end encryption communication. As discussed earlier, our work is inspired from an existing protocol that is very much suitable for a single service provider setting, and we have extended that protocol to fulfill the current requirements of interoperability. Speaking about the protocol, so in the beginning, Alice and Bob both belong to different providers. So they register with their service providers using any of the identity. It can be their phone number or email. That depends upon how the protocol is implemented. A key pair is generated on their device, and the secret key is stored at some local secret location. And the public key is sent from their device to the service provider, where the service provider is generating a Merkle tree, which is basically a name-to-key mapping. The service provider signs the root of the tree with the secret signing key, and this root is published on some public platform, which can be later used by Alice and Bob with the respective providers to verify consistency of their own keys. So now let's see how Bob will establish consistency of Alice's public key. Bob will generate a query message. In that query, he'll put Alice's ID and his own ID. We assume that the client softwares do not talk directly to each other, so all their messages are routed through the providers in between. This query message reaches Bob provider. Bob provider will send that query to Alice's provider, assuming everything is fine. Alice's provider will see that the query is for Alice, so he will generate a response message. The message will consist of Alice ID, Alice public key, and some auxiliary information. He will sign that response message using his secret signing key for the authenticity of the response message. He will then forward the response message to Bob's provider, and Bob's provider will send that message to Bob's device. Now, there is a chance that Bob's provider is trying to manipulate the response message, but in order to pass the verification phase at Bob's device, he has to sign that response message using the signing key of Alice's provider, and we know that that is something which is a secret information known to Alice's provider only. So the response message reaches Bob's device. At first, Bob will verify the authentication of the message received by using the verification key of Alice's provider, which is available as a public information. The next step is Bob will verify Alice ID if it is the same as the one he sent in the query message. And finally, the device will generate the Merkle tree and do the usual steps of verification that I just discussed earlier. After successful verification, Bob can send the encrypted message to Alice through the providers, like first go to Bob provider and then to Alice, and then to finally Alice device. Bob can put his ID in the message so that when the message reaches Alice device, she can see that the message is from Bob, and she can do the same steps for getting Bob's public key. So this is done by all the users that belong to interoperable cross platforms. As we see here, the problem is both the provider knows both points of communication. So speaking about single service provider, because the clients do not talk directly to each other and the communications are routed through single service providers. So it is obvious the service provider know that who is talking to who. But when we talk about interoperable cross platforms, then getting an information about users of different platforms can give information of user base of different service providers to a particular service provider. And he can use that information for business gains, or he can just get an idea about number of users registered with other service providers. And for the users, it is very important that they would like to hide the identity of users who they are talking to with the other service providers, because it can let their service provider know about their social networking patterns. So we extend our protocol to give a privacy preserving interoperable key transparency protocol. So in this protocol, before Bob sends a query for Alice's public key, Bob's device will first establish a Diffie-Hellman key exchange with Alice's provider. Now, both of them have a shared secret between them. Let's see how the protocol works. Now, instead of sending the query as such, the query is encrypted using the shared secret. And as you can see, the query has been modified. Speaking about the modification, we have eliminated Bob's ID from the query message. The reason behind, we don't want Alice's provider to know that who is asking from the other side about Alice. So when this query message reaches Bob's provider, he knows that Bob wants to talk to maybe someone on the other side, but he cannot see whose ID is there in the message. So he'll forward that message to Alice's provider. Alice's provider can decrypt that message using the secret information, and he will generate a response message for Bob. And in this case, instead of signing that response message, he can simply encrypt that response message with the secret shared between them. And when the response reaches Bob's provider this time cannot see what is there in the response message as it is encrypted with the shared secret information. So that information reaches Bob's device. Now Bob will decrypt that information, that message, and he will do the usual verification like verifying the identity of Alice in the query message and do the general steps of verification of like generating the root of the tree and comparing with the one that is available as a public information. After successful verification, when he sends an encrypted message to Alice, he can put his ID inside that message. So the same steps can be done by Alice now. She can establish a Diffie-Hellman key exchange with Bob's provider like that. So now I would like to discuss some deployment considerations of these protocols. Trust between service providers. Different service providers have different key transparency protocols in practice. They have different design policies. They may be using different data structures for name to key mappings. So due to these reasons, they have different levels of trust with other service providers. So it is a choice of service provider whether they opt to do interoperability with other service providers and whether they wish to go with the non-private version of the protocol or the private version of the protocol. Interoperability obligations, as DMA applies to certain set of regions, so it is totally the choice of service providers whether they wish to continue to operate in those regions or they just want to opt out. And speaking about the global service provider, because it applies to certain regions, they can go for interoperability in those regions by providing technical solutions to the other service providers. And they can continue to operate as such they are operating right now in the regions where DMA does not apply. Client software, because interoperability is something which is a mandate on service providers. So we assume that it is the responsibility of service providers to provide necessary code and functions to their client devices so that they can verify consistency of keys of all other users belonging to other platforms with which their service provider is doing interoperability with. But we think that there can be some duplication of functionality or code on the client device. It can add some extra burden as well. So these things have to be considered while implementing the protocol. Spam and abuse. Right now, we have not provided any concrete solution for handling spam and abuse. However, if we see the non-private version of the protocol, both the providers know both the endpoints of the communication. So some solution can be incorporated where the service providers know that who is sending spam and abusive messages or who is adding to the traffic. And in case of the private version, some techniques like message franking can be explored. But yes, currently we think it of implementing as our upcoming future work. Conclusions. So we have provided key transparency protocols for interoperable end-to-end encrypted messaging services. And our protocols provide authenticity, which means any of the service provider is unable to equivocate the public keys using proposed protocol. End-to-end encryption, only senders and receivers of the messages are able to read the messages. Privacy preserving. The privacy preserving version of the proposed protocol provides sender-receiver unlinkability. So that was all from my side, and me and Tariq will be around. If you have any suggestions or feedbacks regarding our work, then just feel free to connect. And right now, I'll happy to have any questions if you have.
Thank you for the nice talk. So we are open for questions. We have good amount of time, so keep it rolling.
Hello.
Hi.
So, what I understood from your motivation, you want to be secure against against both Alice's service provider as well as Bob's service provider being malicious. Well, then, so my idea was, what about the following scenario? Looking at the protocol that you introduced, Alice's provider, when he gets a request, at this point in time, the service provider publishes a new Merkle tree in which he substitutes Alice's public key to something else, and then concerning this, Malt Merkle tree gives the response with a new authentication path back to Bob, and this way the service provider can give a wrong key to Bob. Is there something preventing this in your model or implementation?
Yeah, to your first question, that there's a possibility that Bob is, or if Alice, let's assume that if Alice is checking consistency of her own key, then what if she's getting the right signed tree root updated on the platform? There's a time, there's a chance that service provider is updating that root on the public platform every time when key change happen or a new user join, but that is impractical. That seems very not very much promising solution because lots of users join at a time and key changes are happening frequently. So usually we assume that the keys, the Merkle tree is updated timely. So there's a, and yeah, the keys are updated at certain times. So there is like that. And to your second question, sorry, can you repeat your second question?
So I was thinking of that the Alice's provider responds with a bad key, like not Alice's actual public key, but with a different key, because all that Bob has to verify is the path in the Merkle tree. And if this Alice's service provider, of course, also controls its own Merkle tree.
Yes, I get that.
Responding with a bad key by updating the Merkle tree in the same time or by the time by which Bob verifies.
Yeah. So if Alice server is trying to cheat Bob, so there are two cases in which he can do this. He can maintain different trees, like he's sending some genuine keys to Alice and some other fake keys to Bob. But eventually he will be caught because something which we believe that something which is kept as a public information, it is very hard for service provider to maintain two signed tree roots available as public platform because there may be third parties who are doing auditing. So definitely if the service provider is a big gatekeeper, he's definitely getting caught. And the other way Alice's provider can cheat is he's trying to send some other key not of Alice. But in that case, the consistency test at Bob's device, like when Bob will try to generate the Merkle tree, in that Alice ID is involved. So that will end up in generating very different route than the one which is available as a public information. So in that case also the consistency test will fail. So I hope I answered your question well. Yes.
Just a comment. I mean, in general, key transparency doesn't prevent your provider from giving out bad public keys for your name. The point is that if the provider misbehaves, you have the possibility to find out at a later time that something is wrong.
I'm glad you asked that question. When we were doing this work, all the time from the beginning, we were wondering how to tackle this. Like if something is bad happening, how it is reported and how the users themselves know that their keys are bad, or how the other users tell, for example, how Bob is going to tell Alice that your key is bad, right? So currently we don't see any platform or any form or anything which is provided by the gatekeepers. For example, if I talk about WhatsApp, they provide end-to-end encryption and key transparency, but nowhere we see that how they provide any mechanism that what happens if something goes bad. So definitely we think that if they think that something is not happening bad, but according to us, there must be some logs that are generated when something bad happens, which are sent to, which a user can post to, maybe on social networking like that. So, yeah.